In this lecture, we'll talk about linearity, the property of LTI resistor circuits in general, and we'll talk about superposition in particular. Okay, so let's be precise about what we mean by linearity. More importantly, we'll see how we can exploit that property of LTI resistor circuits. Okay. Now, consider the following scenario. Consider an LTI linear time varying resistance circuit. So all the components are LTI, and resistor meaning that we have LTI resistors, LTI dependent sources, and of course independent sources, and we have possibly ideal transformers in our circuit. So let's output Y, B. Okay. From this circuit, we're interested in, suppose, some particular branch current or branch voltage. Okay, like the current of some resistor or the voltage of some independent current source, things like that. And that particular signal that we're interested in, we're defining as the output of the circuit. Okay, so let output Y be any branch voltage current. Okay, or any branch current, and let the vector U. Okay. Now here we're defining the input vector as follows. We consider all the voltages in our circuit provided by the independent voltage sources together with all the currents provided by independent current sources as our individual inputs. Okay, and then we take all those individual inputs, stack them in a vector, and we call that vector our input vector. Okay, for the circuit. So U1, U2, Un. Okay, suppose that we have n such signals. The input vector whose entries are voltages of the independent voltage sources and the currents of the independent current sources. Independent current sources within the circuit. Okay. Now here is a demonstration of or illustration of what we mean by this definition. Consider a very simple circuit with two independent sources. That means with two separate inputs. Okay. Suppose that this is our circuit. This is a voltage source, independent voltage source, and let this be an independent current source. Okay. IS and VS. And the remaining two are LTI resistors with resistances R1 and R2. So this circuit clearly has four branches, okay, or four components. So that means four voltages and four currents. So we have 8 possibilities for our output. Okay. Each of those individual signals can be taken as the output of the circuit. So let's do the labeling. Plus minus V1, that's the voltage of R1. We always obey passive sign convention and assign the current in that direction as the current of R1. Okay. Likewise, we have plus minus V2, and this is I2. And plus minus V3, and here this is I3, the current of the independent voltage source. And finally, the last and the fourth component we label its voltage and current as V4, like that, and let this be I4. Okay. So we have 4 branch voltages and 4 branch currents, and according to our description here, any one of those 8 signals can be our outputs. Okay, output Y can be any one of the below signals. Okay. I1, V1, I2, V2, current 3, voltage 3, and current 4, and voltage 4. Okay, so that's the output part. How about the input part? For input, we look at the independent sources. We have an independent voltage source here, an independent current source. Together, they constitute the outputs of our circuit. Okay, or you can stack them into a single vector, and that vector you can call the input vector to your circuit. Okay. So input vector we have 2 inputs. The voltage of the independent voltage source and current of the independent current source. Why the voltage on top and the current bottom? No reason, okay, just arbitrary. We could have another input vector where the IS is the first entry and V is the second entry. Okay. So, by linearity, we mean the following. Each output Y, okay, for any one of those 8 signals, let's say, of course we're making a general statement here, not true for just this example, but for any LTI resistance, okay. For each output Y, there exists, okay, a constant row vector, or a matrix, we can say, of size 1 by n, and n is number of our individual inputs in our circuit. For instance, for this example, n is 1 input here, 1 input there, n is 2. Okay, so n. That is, by k we mean a row vector, where entries are k1, k2, kn. Okay, and this row vector is a constant, but is a constant matrix or a constant vector, and it depends on the particular output. For a different output, you have a different K matrix, okay, such that Y equals K times U. Okay. So K is 1 by n, and U is n by 1. U is a vector. Okay. So therefore the product is a scalar, and that scalar is what we define to be our output. Okay. That is, if you write this matrix equation in its open form by remembering that the entries of K are lowercase k1, k2 up to kn, this reads Y of t, that is, the value of the output at any time, equals k1 times the value of the first input at that time, plus k2 times the value of the second input at that time, and so on. K, N, U, N, T. Okay. So, let's return to our example, and for, let's say, this current I1, taken as our output, let's figure out the K matrix, or the entries of the K matrix, that is K1 and K2. Okay, because in this case M is 2, because we have 2 inputs. Okay, example. R1, R2, and here this is our current that we're interested in, our output. For the output, Y equals I, find K1 and K2 such that I equals K1 Bs plus K2 Is at all times. Okay, basically we're trying to figure out the entries of this gain matrix. So let's write KVL at this mesh here, mesh number 1. KVL at mesh 1. Okay. So in mesh 1 we have 3 components. That means we're going to add 3 voltages, and the sum must equal to 0. Starting from this one, we have, okay, we're going plus minus, plus minus, plus minus. So the first voltage is minus. Yes, and then the second voltage is R1 times I, okay, plus minus by Ohm's law, this voltage is R1 times I, and finally we have this voltage, plus minus, and that voltage is R2 times the current passing through it, okay, and what's the current passing through it? Here we have I, here we have Is, therefore by KCL, we apply at this node, this current must be I plus Is. I plus Is, and the sum must equal 0. Now that this equation is in terms of our inputs Vs and Is and our output I. Therefore, we can just rewrite it in this form: y equals, okay, or I equals K1 Vs plus K2 Is. And when we write that, we figure out what K1 and K2 should be. So, what we do is we simply take I to the other side, to the left-hand side. In that case, we can rewrite this equation as I equals 1 over R1 plus R2 times Vs minus R2 over R1 plus R2 Is. Okay. Therefore, this must be our K1, and here this must be the second entry of our gain matrix K2. Hence, K1 equals 1 over R1 plus R2, and K2 equals minus R2 over R1 plus R2. Okay. Now, sometimes it's easier to see the general picture in terms of what we call a block diagram. Okay. It's a technique that, or it's a visual aid that engineers constantly make use of. Okay, so let's try to understand better what's going on in terms of block diagram. Okay, block diagram presentation. Okay, so in this representation, we're going to represent the circuit or our system as a box, and that box will have some arrows getting into it and arrows leaving it. The arrows that are pointing into the box, we call them the inputs, and then the arrows coming out, we call them the outputs. Okay? So this is our linear time invariant resistive circuit. For this circuit, we have a bunch of inputs, okay, or all those inputs, like Vs and S, we can contain them in a vector, and that vector we call the input vector that's driving this circuit, okay? And we're denoting that vector by U. And then from this box, or from that circuit, we extract a piece of information, and that information is what we're calling the output, some branch current or voltage somewhere in the circuit. Now, this is the input, this is the output, and clearly output is a function of input. You play with the inputs, and then the output will change accordingly, and not arbitrarily, it will change according to a rule, and here is the rule, a linear map. Okay. And that, because that map is linear, because LTI, we have the circuit is LTI resistive, it allows us to do certain tricks when we do computation for LTI resistive circuits, like superposition. Okay, so note that Y is a function of U. Okay, the output is a function of U. Not surprisingly, that is. When we write Y, we mean implicitly that it's a function of the input vector U. Okay. Now, a direct implication of linearity is the following. Okay. And later on, we're gonna generalize this observation to dynamic circuits also. In that case, we will also have to consider the initial conditions of the dynamic components along with our external inputs, like the voltages and currents of the independent sources. But that's for later. A direct implication of linearity, or of working with LTI resistive circuits, is Y alpha U plus beta W equals alpha Y U plus beta Y W. Now let's interpret what that equation is telling us. Where U and W are input vectors, and alpha and beta, they are constant real numbers. Okay. So these are signals, they are functions of time, these are constants. Okay. In fact, you can also take them to be functions of time, you can generalize them. But for now, let's take them to be constants. Okay. So this equation tells us the following. Suppose that you have some input that you want to drive the circuit with. Okay, you want to do some experiment. Okay, even though that's true for time varying non-constant inputs, but for suppose that they're constant. Okay, so we have, for instance, input. Okay, that's we have Vs and we had Is. Okay, think about the previous example. First, you have 12 volts, and for Is you have minus 3 amps. Let's say. Okay, so this is your U, and then this U will produce some output. Okay, and that output we're calling Y of U, and then You set the inputs to different values. Let's say this time we have -7 volts here, and then you turn off your independent current source, let's say 0. And this is yet another input or input vector, and it will generate some other output. Okay? And that output, suppose we're calling it y of w. Okay? So you make 2 experiments, one with this set of inputs, the other with the other set of inputs, and each set of inputs generated an output, and that outputs we're calling y of u for the first one and y of w for the second one. So this is u and this is w, if you will. Now linearity allows us to claim that if we make a third experiment, okay, where the input in that third experiment is, let's say, 2 times the first input plus -1 times the second input, okay, 2 times u plus -1 times w, you add them and you obtain a third input vector, okay, and that third input will generate a third output. And that output, it turns out, due to linearity, can be written as alpha times the output that you recorded from your first measurement, plus beta times the output that you measured, that you obtained in your second experiment. Okay. Now we will make use of this very nice property in superposition. That is, that property will allow us to consider one input at a time. Okay, and then we combine our findings to figure out the overall output when all the sources are active. Example. This is our linear time invariant circuit. We have 2 independent sources and 1 dependent source. And the inputs are Vs is fixed at 20 volts and the current supplied by the current source is fixed at 4 amps. Okay. And then what the output for this circuit or the signal that we are interested in is the current passing through the 10 ohm resistor. Okay, we're denoting it by I. Now here, the problem is finding I. Okay, we can find I using techniques that we have talked about, like node analysis or mesh analysis methods. But now we're asked to find I by exploiting the fact that this circuit is linear. In particular, we're asked to find I by superposition, okay, by which we mean consider one input, by which we mean one independent source at a time. Okay. So, what's the input vector for this circuit? The input vector is U equals Vs and Is. Okay, suppose Vs is our first input and Is is our second input. This is clearly a 2 by 1 vector. Okay. Now, linearity implies the following. A gain matrix, let's call it K, K1, K2. It's a 1 by 2 matrix, or you can consider it to be a row vector. Exists and these K1 and K2, they depend on the circuit topology and the parameters, of course, such that the output equals K times U. Okay. So K is 1 by 2, U is 2 by 1, therefore the product is 1 by 1, a scalar. And that scalar is our current, the output. Okay. Now, we can write the following. Now, we don't know what K is, but we know that such a K exists. And that knowledge is itself valuable, even without knowing what K is. Because using that piece of information, we can generate the following reasoning, which is quite helpful. We can write the following. I equals K times the input. And input is this vector, Vs, Is. Okay? This is for general. We don't have to confine ourselves to the given values of Vs and Is. Anyway, so this thing can be written as K times any sum of vectors where the sum equals this Vs, Is input. One of those particular sums, okay, that's quite interesting, is the following. Is such that only one of the entries is non-zero. Okay. For instance, this we can write as Vs0 plus 0 Is. Clearly, this plus that give us Vs, Is, the original input vector. Okay. And that, because this is simply matrix multiplication, we can write this as, we can use the distributive property, and we can write that as K times Vs0 plus K times 0 Is. Okay. Now, this is just straightforward mathematics, but its physical implications is quite important. So let's call this number I1. Okay, I1. And let's call this scalar I2. Okay. Now let's talk about the physical importance of those two numbers, I1 and I2. Now, I1 is the following. Now, if you forget about this term and only concentrate on that, I1 is the current that you will obtain when you excite the circuit with Vs only, okay? That is Is equals 0, meaning that this is turned off and the only thing that's driving the circuit is Vs, okay? In that case, that Vs will generate some current at the output, and that current we're calling I1. Now we do the same thing to Vs, that is, we turn off Vs, okay? We are killing Vs, and then only Is is active, and that input will generate some output, okay? And that output we're calling I2, okay? And linearity of the circuit allows us to add this number to that number, I1 and I2, and the sum should give us the output when both sources or both inputs are active simultaneously. Okay, and that thing we call it superposition, considering one source at a time. So I1 is the current passing through 10 ohm resistor when Is equals 0. Okay. When independent current source is killed. Okay. So turning off a source, independent source, sometimes is indicated by using the word to kill. Okay. I2 likewise is the current passing through 10 ohm resistor when the voltage source is killed, when Vs equals 0. That is, when the independent voltage source is killed. Okay. Now, the reason that this is an important observation is because when you kill some of the inputs, when the circuit is left with just a single input or single independent source, usually it's much easier to figure out or to do computations, okay, on that circuit. Therefore, this superposition allows us to develop a straightforward, easy method, okay, to compute some given output in a circuit. Now, to compute I1, let's kill the current source. Ix 10 ohm, I1 15 ohm, Ix, and Vs was given to be 20 volts, Is was 4 amps, but now we are considering the case where Is equals 0. So that's what we mean by killing an independent source, making it provide 0 current or voltage. Okay? Here we have 0 amps. Now, one nice thing about a 0 amp current source is that it can be represented by something very cheap, a very cheap component. Note that at all times, regardless of the voltage that may appear across the terminals of this independent current source, it always provides 0 amps. Okay? That is, it never allows any current to pass through this wire. But we know another component that's very simple, it's not a current source, that does exactly the same thing, and that component is no other than the open circuit. Therefore, this is equivalent from any point of view to the following configuration. Okay? An open circuit. So, therefore, killing an independent current source means replacing it with an open circuit. Note that once this is replaced by an open circuit, all of a sudden the circuit became much simpler. It just has a single loop, and a writing caveat in that single loop will directly give us what we want, which is I1. And then what we're going to do, we're going to kill this source and do something quite similar. Okay. So by KVL, we have, okay, let's write the voltage equation in this loop. Minus 20 plus 15 Ix plus 10 I1 minus 5 Ix equals 0. Okay? And since this is open circuit, clearly this Ix and that I1, these two currents are the same. Okay? That is, Ix is no other than I1 because this source is killed. Therefore, this equation becomes only in terms of I1 if you replace Ix with I1, and that gives us 20 I1 equals 20. In other words, I1 turns out to be 1 amp. Okay. So we have computed I1. Let's compute easily because one of the sources were gone. Now we're going to compute I2 almost as easily, and then superposition will allow us to add the two numbers to obtain the overall answer. Compute I2, kill this time the independent voltage source. Okay. Or amps minus plus 5ix, ix, 15 ohm, 10 ohm, and now we're after this current. Now this is our independent voltage source, and in this configuration we're killing it, meaning that we're replacing it with a voltage source that provides 0 volt. But we know a very simple component that does exactly this. That is, at any time, the current passing through that voltage source could be anything, but this guarantees that, makes sure that the voltage drop across its terminals is always 0. And that we can do exactly the same thing by replacing that voltage source by a short circuit. Okay. So that's what we mean, or what's equivalent to killing independent voltage source, replacing it with a short circuit. Okay, so KVL. Again, you write KVL at the outer mesh. Now what we have is this voltage plus that voltage equals 0. Here we have 15ix plus 10i2 minus 5ix equals 0. This time ix and the output current are not the same, but their relation is very easy to see. Okay, ix plus 4 equals i2. Therefore, ix equals i2 minus 4. So we can express ix in terms of i2, replace that ix with this expression, and then the equation becomes only in terms of i2, and then we can easily solve for i2. Okay. This time we have 20 i2 equals 40, which gives us i2 equals 2 amps. Okay. So I1 equals 1 amp when one of the sources is killed, I2 equals 2 amp when the other source is killed. Therefore, when both sources are active, that is, when nothing is killed, then the overall output must be, because circuit is LTI, resisted, the overall output must be this number plus that number, namely 3 amps. Okay. Finally, to find we superpose, okay, the two currents, I1 and I2. I1 plus I2, and that gives us 3 amps. Okay, so that's the current, or that's the output that we will measure when both sources, independent sources, are active. So once again, we computed some output using superposition, and to be able to do that, what we did, we killed a source at a time, and then we worked on the simpler circuit. Then we added the overall, the individual answers to find the overall answer. Okay. So remember that killing an independent voltage source means that replacing it with a short circuit, and killing an independent current source means that we replace it with an open circuit. Okay. As for dependent sources, they are not inputs, okay, so it's killing them is out of the question. You never touch dependent sources. Okay, let's now move on to another example. Suppose that 3 experiments are performed on the globe circuit. So this is our circuit. Clearly it's LTI resistive. Therefore we can apply or we can exploit the linearity property. How many inputs do we have? We have 2 independent sources. One is an independent voltage source, other is an independent current source. Therefore the individual inputs are Vs provided by that voltage source and Is provided by this current source. We have a dependent source, but we said that the voltages or currents provided by dependent sources, we don't consider them as inputs. Okay. And the output for the circuit or the signal that we're interested in is the voltage that appears across the terms of second resistive part. Now the experiment, the results from experiments are given in the following table. Experiment 1, experiment 2, and experiment 3. Vs, the first column is for the first input, the second column is for the second individual input, and the third column is for the output of this circuit. Okay. In the first experiment, the voltage is 12 volts, Is is open circuit, or providing 0 amp, and you measure some voltage, and that voltage is labeled V1. In the second experiment, the voltage of the independent voltage source is -6 volts, and Is is the second input is 6 amps, and some voltage is measured at the output, and that's labeled as V2. And in the third experiment, we have 4 volts, 4 amps, and the corresponding output is labeled as V3. Okay. Now the question is, express V3 in terms of V1 and V2. And the story that, or the scenario that might go with this purpose or this goal is the following. Suppose that this circuit represents some system, and it's suppose that it's quite expensive to perform experiments, okay, on that system, and therefore you want to perform as few experiments as possible. So you perform the first experiment, you obtain some reading. You perform the second experiment, you obtain yet another reading, V1 and V2, and also you need the following reading, V3. Okay, but instead of performing a third experiment, you can use the linearity property of the circuit to compute V3 by the previous information, V1 and V2. And let's see how we can do that. It turns out that to compute that, you don't even have to know what's R1, R2, this lowercase r. You don't have to solve the circuit. All the information that you need is in this table, plus, of course, the knowledge that the circuit is LTI resistive. Okay, so let's proceed to figure out V3, assuming that V1 and V2 are known. Okay, solution as follows. By linearity, because the circuit is LTI resistive, there must exist a gain matrix K. Okay, it's 1 by 2, because we have two individual inputs, such that V equals K times Vs Is. Okay. K times Vs Is, the product is 1 by 1. It's our scalar out. So let's express experiment 1 in terms of that matrix, which at this point we don't know. Experiment 1 means that V1 must equal K times, this is our gain matrix, we don't know what it is, but for experiment 1 we know the input vector, because it's given in the table. Vs is 12 volts and Is is 0. 12, 0. So whatever K is, V1 must equal that K times this vector 12, 0. And experiment 2 means, or implies, that V2 equals K times the input vector that is used in the second experiment, and the input vector that is used in the second experiment is -6 for the first entry and 6 for the second entry. -6, 6. Okay. Now, these two individual equations can be put into a single equation. Okay. So we can write V1, V2 equals K times a 2 by 2 matrix, where the first column is coming from this equation, second column coming from the second equation. 12, 0, and -6, 6. Okay. All we did is we wrote down these two separate equations as a single equation. And then from this equation we can pull K by multiplying both sides from right by the inverse of this matrix. Therefore, K equals V1, V2 times the inverse of that matrix. 12 -6, 6, 0 inverse. Okay, so therefore, if V1 and V2 were known, then K can be computed from these two experiments. And once we have K, we can compute V3 by multiplying the vector 4, 4 by that gain matrix K. Okay. So let's do that. Now let's interpret experiment 3 in terms of, again, the gain matrix. Experiment 3 implies the following relation. V3 equals the gain matrix times the input vector that's used in the experiment 3, which was 4 volts and 4 amps. 4, 4. That equals V1, V2 times the inverse of that matrix, which can be computed to be 1/12, 1/12, 0, 1/6. Okay, so this thing here is K, our gain matrix, and by K we're multiplying 4, 4. And now we can multiply this matrix with 4, 4, and that gives us 2/3 and 2/3. Okay. Therefore, V3 must equal V1, V2 row vector times 2/3, 2/3 column vector, which is 2/3 V1 plus 2/3 V2. Okay. So that means if you already performed experiment 1 and experiment 2, and if you also need to figure out the voltage, the output, when the input is 4, 4, you don't have to perform the third experiment. You can easily compute V3 through this linear combination of the first two results. 2/3 V1 plus 2/3 V2. Okay. Now here's another way. It's not really different, but let's also put it down. Or, okay, V3 equals the output when the input is the vector 4. Okay. So V was the general notation that we used to indicate our output, and V3 is the value of the output for the third experiment, and the input for the third experiment is this vector 4, 4. Okay. Now, suppose that we can write this vector 4, 4 as a linear combination of two other vectors. Okay. V equals alpha times 12, 0 plus beta times minus 6, 6. Okay. Now, these two vectors you will immediately recognize are not just arbitrary vectors, but this is the vector that corresponds to the input for the first experiment, and this is the vector that corresponds to the input for the second experiment. Okay. And the question now is whether can we find alpha and beta such that alpha times this vector plus beta times that vector gives us 4, 4. Okay. Why? That would be a nice thing to do, to be able to do. The reason is as follows. So that equals what? Because the input-output relationship is linear. This this expression can be written as the following: alpha times V 12, 0, okay, plus beta times V minus 6, 6. Okay. Now that this is, according to our notation, is the output that you measure when the input is 12, 0. And that's exactly the output that we measured for the first experiment. And this expression here is the output that you obtain when the input is minus 6, 6. And this is no other than V2, the measurement of the second experiment. Okay. So this is therefore alpha V1 plus beta V2. Therefore, the question or the problem now becomes the following: whether we can find alpha and beta such that when we write these two vectors in the following linear combination, they give us 4, 4. If we can find such alpha and beta, those alpha and beta we can use here to obtain the linear combination from V1 and V2, and that linear combination must equal V3, the output of the third experiment. Okay? So let's consider this, therefore, this being equal to 4, 4. Alpha 12, 0 plus beta minus 6, 6 equals 4, 4. Okay. So we're interested in figuring out alpha and beta. Let's write them as individual equations. 12 alpha minus 6 beta equals 4. 0 alpha plus 6 beta equals 4. Okay. This gives beta equals 2/3, and using that beta we can figure out alpha, which also is 2/3. Okay. Alpha equals 2/3 and beta equals 2/3. Okay. As expected, because we already computed alpha and beta here as V 2/3.